We've explained the pole in the barn paradox. We understand how the relativity of simultaneity allows each perspective to understand the other's view regarding whether or not the pole fits. But it still may leave you with a question. When I first learned about this pole in the barn paradox, it still left me with a question, which is this. What if you have a barn that has doors, let's say steel doors, right? And as that pole is coming in, when you say that it's inside, bam, you shut those steel doors. Wouldn't that prove that your perspective is the right perspective, that the pole really does fit inside the barn? Well, yeah, it would establish your perspective that the pole fits, but now you've pretty much changed the problem, right? Because if you have these steel doors, then the pole is going to slam into it, which means it's going to no longer be moving at constant velocity. It's going to experience an acceleration, or in this case, actually a deceleration as it slams in. And then all sorts of issues come into play, because if you try to accelerate an object, well, there's no such thing as a fully rigid object in the world, right? So if you push on anything at all, the push that you exert, the force you exert, has to travel through the object so the back knows that the front has been pushed, and that can cause a compression of the object. Or if you're pulling on it, that can cause the object to stretch. So you really have changed the problem, but nevertheless, it's an interesting problem to raise. Can we work out exactly what would happen in this situation? So we're going to give a model for the idea of causing the pole to stop when it's inside the barn. And we're going to give a mathematical model for that in a moment. But let me first give you the essential idea, which is really just what I was mentioning. From the perspective of the barn, boom, they shut the doors at the same moment. Good. What will the perspective of the pole be? Well, from the pole's perspective, of course, the clocks in the barn frame of reference are not in sync with one another. So the pole is coming in, which means the barn is going this way, which means the clocks in the back are ahead of the clocks in the front from the pole's perspective, which means they claim, boom, the back door closes first, the pole comes in, it compresses, then the front door is closed. That's why, from the pole's perspective, it now fits, where previously the pole said that it didn't. Now, I'd like to take that idea and make it a little bit more mathematical, and to do that, I need to commit to some very specific way of stopping the motion of the pole. Because to understand this compression effect, we really need to understand the details of how the pole is brought to rest. And here is the method. And the reason I'm going to use it is because it's particularly simple for the calculations. The method I'm going to use is not literally steel doors. We could do that, it's a little bit more complicated. Instead, let's imagine that Gracie and all her friends in the barn frame of reference are standing there, waiting for the pole to come in. And they agree that when the pole is inside, at an appointed moment, they will simultaneously grab hold of it, instantaneously from their perspective, bringing the pole to rest. That gets rid of some of the issues of rigid bodies if we're going to grab it from the barn's perspective all at the same moment. That's how we are going to describe the pole being brought to rest. What will the pole perspective be, right? So I'm now going to be the pole. From my perspective, here I'm standing. The barn is coming toward me, which means that the clocks far away are further ahead in time, which means as the pole comes in, I'm going to claim, if I stand this way, that first someone in the barn grabs this point, then 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 this point, a wave of grabbing of the pole, not at the same moment in time, because I have a different conception of simultaneity if I'm moving with the pole. And what I'd like to do is do a little calculation right now of what would happen to the pole in that circumstance. If it's grabbed here, then grabbed here, then grabbed here, then grabbed here. Now the issue of compression comes into play. If the pole is grabbed here, this part continues to move. Then it's grabbed, but this part continues to move, and then it's grabbed. And because of that, there will be a squeezing down of the pole. And that's why it will now fit. Let's do the calculation to see how that actually goes. All right, so let's look at our pole. So here is a picture of the pole. And from the pole's perspective, what happens is different parts on the pole get grabbed at different moments. So let's indicate that. So from the pole's view, the barn is moving that way, which means that this guy over here is grabbed first, according to the pole. This guy over here is grabbed second, third, and fourth, and say this guy over here is grabbed last. And I want to focus in on one little chunk of the pole. Let's just look at one piece right in there, and let's call that length, say, delta L naught. That's the length of that little chunk. And I'm now going to apply this idea that the left side is grabbed first relative to the right side to calculate how much it squeezes down. How do I do that? Well, let's calculate the time difference. Well, the time difference between the grabs. Well, we know what that time difference is. From the perspective of the pole, the barn is moving this way, which means the clocks on this side are earlier by an amount that is given by the velocity of the barn from the pole's perspective times the distance between the two clocks. And the distance between those two clocks, say, is equal to delta x. And you take that and divide through that amount by c squared, where this is the distance between the observers that are grabbing the pole in the barn frame. Okay. Now, given that, we can then work out that that amount, delta L naught, will get squeezed. It'll get squeezed by the amount that this part of the pole moves before it gets grabbed. This guy gets grabbed, then this guy gets grabbed. The time difference times the speed is how much it'll squeeze down. So you start with that length, you subtract off the velocity times the time, which is v times delta x, divided by c squared. Okay, so what is the value of delta x? So delta x is just this guy delta L naught. So this then is equal to delta L naught times 1 minus v squared over c squared. And we recognize that as delta L naught times 1 over gamma squared. Now that happens to each and every chunk of the pole. Each and every chunk of the pole gets squeezed down by the amount that the right-hand side moves after the left-hand side has been grabbed, right? So if you take account of that over the full pole, that means L naught itself, the length of the pole from the perspective of those who are moving with it, will go down to L naught divided by the same factor, gamma squared. So according to the folks in the pole frame of reference, this procedure of grabbing the pole, because from their view it does not happen simultaneously, results in the pole being squeezed down. And it's squeezed down by a sufficiently large factor that now the pole people completely understand why the pole fits. It's not a mystery any longer, not a matter of different perspectives. It has been squeezed down. Now, I want to ask you, though, does this answer make sense relative to everything else we know? And the answer is it does. Why do we get the answer L naught over gamma squared? Well, think about it. From the perspective of those in the barn, so the barn people, they say that the pole's length is L naught divided by gamma, because from their view it is length contracted. When they grab hold of it instantaneously, therefore, this is the length of the pole that they expect, and this is the length of the pole that they would get. So why do we have an extra factor of gamma over there? Well, let's think about it. This, of course, is the perspective from the pole frame of reference. And after the pole is brought to rest in the barn, right, the pole frame of reference, the guys who were initially moving with the pole, they aren't stopped. The reference frame isn't stopped. The reference frame continues to move. So now, after the pole has been brought to rest, the pole people say that the pole has velocity v. And if the pole has velocity v, then it gets length contracted from the perspective of the pole observers. So it has length L naught over gamma in the barn frame, but the pole frame is moving relative to this, so it gets length contracted by an additional factor of gamma, and therefore, indeed, the result L naught over gamma squared is exactly what we'd expect to find. So the way to think about this is the one factor of gamma you can think about coming just from ordinary Lorentz contraction. This additional factor of gamma comes from the compression of the pole, at least from this frame of reference. So there you have it. We can model how we bring the pole to rest. Indeed, it will fit inside the barn. From the perspective of the pole observers, though, there's a reason for that. The pole has been crushed. It has been shrunken down by a compression factor because it was not grabbed simultaneously. The parts on this side continued to move after this side was brought to rest. So that's how you can understand the pole in the barn paradox if you go this next step and consider stopping the pole inside of the barn. It all makes perfect sense, with L naught over gamma squared being the resultant length of the pole after it is brought to rest in the barn's frame of reference. So Lorentz contraction and compression explain what happens in this version of the scenario.